So, okay, students, in the last class, we completed the normal incidence at a plane of conducting the boundary and dielectric boundary. We completed the both. Now, we go for the next one is oblique incidence. Oblique incidence at a plane of conducting boundary. Okay. So, oblique incidence. At a plane of conducting boundary. So, conducting boundary means there is no any transmission because of eta is equal to 0. We know the transmission coefficient tau is equal to 2 eta 2 by eta 2 plus eta 1. So whatever the incident beam is there in the z direction, fully it is reflected. Okay. At a plane of conducting boundary. I'm taking the conducting. Okay. So listen carefully. Here we have the right angle triangles we get in the oblique incidence. For the normal incidence, it is not. Okay. Conducting boundary means the left hand side is a dielectric. With having the parameters epsilon 1, eta 1, and the sigma 1 and mu 1 like that. Conducting also for that same thing. Conducting boundary. So for the difference, we shade this conducting boundary. Okay. Now I'm taking a beam, electromagnetic beam is incident obliquely with an angle of theta I. Here we have to know, first of all, is a horizontal polarization. Horizontal polarization means the electric field vector is perpendicular to the plane of incidence. Electric field is perpendicular to the plane of incidence. So I'm taking here the EI. EI is perpendicular to the plane of incidence, and HI is parallel to the incidence beam. The horizontal polarization means electrical field vector is perpendicular to the plane of incidence. The plane of incidence electrical field is 90 degrees. But the electric field vector is aligned parallel to the boundary surface. This is a boundary line between dielectric and dielectric. Whenever you are comparing with this boundary line, the electric field is parallel. Whenever you come comparing with the incident beam, the electric field is perpendicular, then we can call it as a horizontal polarization. Horizontal polarization. Electric field is perpendicular to the incidence beam, or electric field is parallel to the aligned parallel to the boundary surface between dielectric and the conducting. Okay. And what is a vertical polarization means? Vertical polarization, magnetic field is aligned parallel to the boundary of the surface, or magnetic field is perpendicular to the plane of incidence. And you have to remember only about the perpendicular to the plane of incidence. Horizontal is electrical field is perpendicular, and vertical polarization, magnetic field is perpendicular to the plane of incidence. Okay. And when comparing with the boundary surface, electric field is parallel with the boundary surface. We can call it as a horizontal polarization. Magnetic field is aligned parallel to the boundary surface. We can call it as a vertical polarization. Okay. Since the boundary surface is between the dielectric and the conductor, there is no any transmission. The fully it is reflected with an angle of theta r. With an angle of theta r, and ER, HR. Always a H and the E, electric field and the magnetic field is both are perpendicular to each other, and the wave is traveled through the Z direction. Okay. And coming to the vertical polarization, if I am drawing here, the vertical polarization is vertical polarization. It is also in between of dielectric and conducting boundary. Okay. So there is some difference to change as a conducting medium. Here is a shaded part. Now see what we are saying, the vertical polarization and the horizontal polarization means in horizontal polarization, electric field is perpendicular to the plane of incidence, or otherwise that same electrical field is aligned parallel to the surface of the boundary surface between the dielectric and the conducting. Vertical polarization is related to the magnetic field. Okay, I'm taking the incidence beam, then angle of theta I. Here, so magnetic field is perpendicular to the incident beam, HI here, and not in this side. So HI here and EI. Okay, EI is aligned parallel to the magnetic field is aligned parallel to the top of the boundary surface. Okay, because it is conducting medium, there is no any transmission. Fully it is reflected. Fully it is reflected, and we have the EI here, not the EI, ER, and the HR. Okay, with the theta R. Here also the theta R is there. Okay, now we compare these two, the vertical polarization and horizontal polarization in the oblique incidence at a plane of a conducting boundary. So what is the difference here? When we call it as a horizontal polarization and when we call it as a vertical polarization means the EI, you see here, the EI, the electric field vector is perpendicular to the plane of incidence, is called horizontal polarization, and vertical polarization is magnetic field HI. The magnetic field vector is perpendicular to the plane of incidence, perpendicular to the plane of incidence is called vertical polarization. Okay, when magnetic field is perpendicular means definitely the EI is parallel to the boundary condition. So we can also call it as vertical polarization means electrical field is aligned parallel to the boundary surface. And horizontal polarization, EI is perpendicular to the plane of incidence, means definitely that is HI. HI is parallel to that of the incidence beam. Forget about all this. If any confusion is there, simply we can say horizontal means electric field is perpendicular to the plane of incidence is called horizontal polarization. And magnetic field is perpendicular to the plane of incidence is the vertical polarization. The incidence beam is with an angle of theta I because it is oblique incidence. We taken that is a boundary between the dielectric and conducting. There is no any transmission when there is an incidence beam with an angle of theta I. Fully it is reflected in opposite direction with an angle of theta R because of it is an oblique incidence. So only the difference you can show on the incident beam is theta I and the reflected beam is theta R in the both horizontal and vertical polarization. But the places of the electric and the magnetic field is different. In horizontal, that is perpendicular in the incidence beam. Now in the vertical polarization, the magnetic field is perpendicular to the incident beam. That is a difference here. Okay. Now by using these diagrams, you can find out the reflection coefficient and the transmission coefficient. Transmission coefficient, as usual, it is a 0 here, the conducting boundary. And what is the reflection coefficient and how we can find the intrinsic impedance also from this horizontal polarization and the vertical polarization. First, you can go for by using the horizontal polarization. Horizontal polarization. Since this is in the ANI bar direction, there's a vector, it is EI bar. And having the ANI bar, the direction it shows unit vector. Similar way, the ANR bar is a direction of when can electric field or the magnetic field is as considered as a vectors. HR and the ER and EI bar and the HI bar. Okay. Okay. It's ANI bar. Now, how we find this ANI bar? By using this right angle triangle, we can consider it as, say I'm drawing a perpendicular line here, a dotted line on the incident beam. So theta I is here, the whatever I drawn a perpendicular line on the incident beam is opposite side. So it is a sine theta I. It's a sine theta I. And here adjacent side is a cos theta I. Cos theta I. This one. Okay. And this is a hypotenuse. Similar way, I draw a perpendicular line onto the reflected beam. For theta R, you see the theta R here. See. This is a cos theta I. Theta R. Opposite side is a sine theta R. And this one is a sine theta R. And adjacent side is a cos theta R. So the same line we have the cos theta R and the cos theta I. So theta I is equal to theta R. Just to remember that one. You can call it as Snell's law of reflection of the theta r is equal to the theta I. By using these two right angle triangle, you can write the ANI bar. So what is the ANI bar is equal to the horizontal polarization. ANI bar is equal to, by the right angle triangle. So there is sine theta I. Every time you can start where it is started the incident beam. So there is a point, it is a started point, and end is a boundary surface. So it is in the above direction, shows Z. Okay, this is a Z direction, and this one is a Y direction, and there is a X direction is there. So above line is a Z direction, not the Z, it is a, let us say, the X axis. This is the X axis, because X axis and this is Z direction, Z axis, and if it is another one is a Y direction. Okay, the electric field is parallel to that of a boundary surface. We can call it as a horizontal polarization. So x-axis means it traveled from this point to the above, means it is AX. It's a positive AX. Okay. So sine theta I into, because it is in the forward direction, AX bar, ANI bar is equal to sine theta I into AX bar. And coming to here, from this point, it is traveled towards the Z direction, is a positive direction only. That positive direction is a cos theta, adjacent side is a cos theta. So cos theta I into AZ bar. Okay. Similarly, I have to write the ANR bar also. ANR bar is equal to, by using this right angle triangle here, the reflection coefficient, reflection beam is started from the boundary surface here. You take from here itself and move towards negative direction of Z and move towards a positive X direction. So move towards the negative Z direction. What is the adjacent side here? The cos theta R. So cos theta R into minus AZ and sin theta R into plus AZ. Okay, you can write that as equation also. ANR bar is equal to cos theta R into minus AZ bar plus sin theta R into AX bar. AX is in the positive direction. AZ is in the negative direction for the reflected beam, when we can consider it as a line drawn on the reflected beam. To get it is a right angle triangle. Opposite to the theta R is a sin theta R and adjacent side is a cos theta R. To find out, to write the equation of ANR bar, nothing but unit vector. It is started at the boundary surface and move towards negative Z direction with a cos theta magnitude, and from there it moves positive X direction with the magnitude of sin theta R. ANR bar and ANI bar we got. If any ANT is there, the transmission beam is also there, we get the ANT bar also. Okay. So in the left hand side, according to the boundary conditions between the dielectric and the boundary, so E1 bar is equal to E2 bar. E1 bar is equal to E2 bar. And what is the E1 is a combination of electric and incident and the reflection. EI bar plus ER bar is equal to, actually if there is any transmission is there, the transmission ET bar. For dielectric and the conductor there is no any transmission, so EI bar plus ER bar is equal to 0. Simply. And EI bar is equal to, what is the EI bar now? EI bar is equal to having the magnitude is EI and it is traveled, the wave having the phase is there, e power minus j beta 1. Why I'm taking it is a beta 1, the dielectric 1, it is a 1 with z value, actually it's a beta 1 into z. That z is nothing but a constant value with ANI bar dot R bar. Okay. What is the ANI? We have the sine theta into x bar plus cos theta into AY bar. And this is in the y direction. Okay. Y direction, AY bar. That is equal to EI into e power minus j beta 1. Actually, it is a z. Z is nothing but ANI bar dot R bar. That R bar is equal to, because it's the Cartesian coordinate system, we consider it as R bar is equal to, also you can write as R bar is equal to x into AX bar plus y into AY bar plus z into AZ bar. Z into AZ bar. Now, the dot product between of ANI and the R, having the AX is there and AZ is there. There is no any AY coefficients in the ANI bar. So, we didn't get any AY. The sine theta I into x, sine theta I into x will get as x into sine theta I, AX bar dot AX bar is equal to 1. Okay. Applying the dot product for this ANI bar dot R bar, AX bar dot AX bar is equal to 1. So what is the coefficient? The product of x into sine theta I, x into sine theta I. And there is no any y term is there. We didn't get any y term, and the z, AZ bar, that AZ bar. And coefficient is the product of z into cos theta I, and AY bar, EI bar is equal to. Okay, so we got the EI bar is equal to, so one equation, EI into e power minus j beta 1 x sine theta I plus z into cos theta I. Okay. And similar way, you can find out the magnetic field also. What is the magnetic field? HI bar is equal to, HI bar is the actually the ratio between of the magnetic field and the electric field is intrinsic impedance only. Now, you can apply a cross product ANI cross E1 bar whole divided by the eta 1. Why I am taking the eta 1? Because it is in the left hand side. The parameters are is a N1, eta 1, and the epsilon 1, and the mu 1, sigma 1 like this. Okay. HI bar is equal to ANI bar cross E1 bar by the eta 1. The eta 1 is a ratio between of EI and the HI only. This is not the E1, EI it is. EI bar. Okay. That is equal to. Now I am taking the EI bar and apply the cross product of A and I. Take it as EI into e power minus j beta 1 into, what is the power having, x into sine theta I. So carefully observe, my dear students. Sine theta I plus z into cos theta I. And here there is an AY bar is there. AY bar. And this totally it is the magnitude cross. Okay, I substitute the AI bar That is EI bar is the total function EI into e power minus j beta 1 x sine theta I plus z cos theta into AY bar. Okay, AY bar cross ANI bar. What is the ANI bar here? Sine theta I into AX plus cos theta I into AY. Okay. I'm taking here sine theta I AX bar plus cos theta I into AZ bar. Okay. And whole divided by is eta 1 actually. Okay. This is the equation now. The HI bar is equal to. Now simplify or apply the cross product of ANI AY bar cross AX bar. Okay. AY bar cross this fact function, or actually it is in the ANI cross EI bar. So AX cross AY and AZ cross AY. It's very important. In the formula itself, it shows that it's ANI cross EI. So first of all, you can write it as ANI, then you can write the EI. Okay. But I wrote in the first one is the EI and next one is the ANI bar. So you can take it as a cross product of AX cross AY. AX cross AY and AZ cross AY. Okay. So HI bar is equal to, now it becomes of HI bar is equal to EI by eta 1. Take it as e power minus j beta 1 x cos sine theta I plus z cos theta I whole multiply with, and is a whole multiply with this product. What is the product here? AX cross AY. Why I'm not taking the AY cross AX means I wrote it is a cross product is ANI first of all. AX AY means it is in order only. So sine theta I into AZ bar. The cross product is always, you can see X, Y and Z. If it is a AX cross AY means we'll get the positive Z. AY cross AZ means we'll get the positive AX. AZ cross AX means we'll get the positive AY. But in the reverse order, AY cross AX means minus AZ will get. AZ cross AY means it is in the reverse direction, so a minus AX will get. Like that. AX cross AY means it is in the order only. Sine theta I into AZ bar, because I am applying the cross product AZ bar. AZ bar. Okay. And now see the AZ cross AY. AZ cross AY means it is not in the order. Minus AX will get. So minus cos theta I into we're applying the Z and Y, you get the AX cross minus AX. Okay. So that is a HI equation. We got the EI bar and the HI bar, the two equations, electric and the magnetic fields. See, no need of this, all the calculations here. Whatever the EI we have, EI into e power minus j beta 1 x sine theta I plus z cos theta I, and what is the multiplication factor you have to take from the right angle triangles. Apply a right angle triangle here. See, I draw a perpendicular line and also this one. Let's assume this is a right angle triangle here. The theta I, and for this theta I, there's a sine theta I is opposite direction, opposite side, and cos theta I is here, cos theta I. So from this right angle triangle, it starts from the EI here and it moves towards the negative direction of the X. See, from this right angle triangle, it moves towards the negative direction of X. The positive direction is upwards, X direction. For X axis, the positive direction is in the upwards, and now it is in the moves towards the negative direction. So negative direction means cos theta I into minus AX bar. See, we got the same thing. Cos theta I into minus AX bar. And after this, it's travel and moves towards the Z direction, that is a positive Z direction, with the magnitude of sin theta I. Sin theta I into AZ bar. You see, that is only we got the sin theta I into AZ bar. So no need of doing all this cross product here. Simply whatever the magnitude is there in the EI bar, AY bar is the direction. Magnitude is EI into e power minus j beta 1x sin theta I plus z cos theta I, and multiply the equation what we got from this right angle triangle, what we write drawn here. Whatever the multiplication factor, you have to multiply that with the magnitude of the electric field, simply. Okay, without any direction, AY bar. That AY bar cross this function cos sin theta into AX bar and cos theta into AZ bar only, will get the same function. The similar way, we got the EI and the HI. You can find the ER and HR also. So what is the equations we got to the ER and the HR? Same thing. ER bar is equal to ER into e power minus j beta 1 only, because it is in the left hand side. Beta 1. ANR bar. Now it is ANI bar. Change it as ANR bar dot R bar. What is the ANR bar? We have this equation is there, cos theta R minus AZ bar and the sin theta R into AX bar. Apply the dot product there with the R bar to see what is the function we'll get in the parenthesis of the power of e power minus j beta 1 sin theta R into AX. So X into sin theta R, and cos theta R of minus AZ is here. So Z minus Z into cos theta R. So EI is equal to, not the EI, ER is equal to. Let us see that also. ER is equal to, ER bar is equal to, the magnitude is ER, and e power minus j beta 1 into ANR bar dot R bar along the direction of AY. Along the direction of AY only. What is the ANR bar is equal to? So ER into e power minus j beta 1, the dot product, see the dot product of these two, ANR bar and R bar. Sin theta R into X. So X into sin theta R. And AZ and ZZ is the dot product is 1, and the product is Z into cos theta R with a minus sign. So minus Z into cos theta R. Cos theta R into AY bar. Actually, is the ER bar is equal to, we got one equation, ER bar is equal to e power minus j beta 1, e power minus j beta 1 x sin theta R minus Z into cos theta R into AY bar. What is the HR bar is equal to now? HR bar is equal to, following the same function, the ER by the eta 1 e power minus j beta 1 x sin theta R minus Z cos theta R, and don't write the AY bar here, that is a dot product of that function ANR bar, otherwise directly write the equation from the right angle triangle what we get here. See, this is a right angle triangle with the theta R. See, we started at the ER here and moves towards AX is adjacent side. Okay, adjacent side. So cos theta r into AX bar. Cos theta r into AX bar and sin theta r into AZ bar. Okay. Is whole multiplied with cos theta r is adjacent side and it moves towards the positive x direction, cos theta r plus into AX bar plus and sin theta r opposite side into AZ bar. This is the equation we got. We'll get after applying the cross product of AY and ANR bar. Otherwise, you can see that if any confusion, AY bar cross ANR bar. Okay, for this function into cross AY, AZ and AY, AZ and AY is nothing but it is in the reverse direction. Minus AX, already here the minus is there. Plus, so cos theta r into AX. The same thing you'll get, cos theta r into AX. And AX cross AY. AX cross AY is in order sin theta r into AZ bar only. So sin theta r into AZ bar. So no need of again apply that it is a ANR bar cross AY bar, but draw a perpendicular, not the perpendicular, a right angle triangle for the theta r at ER bar with the HR bar is a hypotenuse, and in the below of EI also that HI is a direction towards is taking it as a hypotenuse. By using that right angle triangle, whatever the equation we got, that is multiplied with the magnitude of the EI, ER bar or EI also. To get HI, whatever the magnitude of EI, multiply this equation from the right angle triangle, and for HR, take the magnitude of ER and multiply the equation whatever we got from the right angle triangle. Okay, so we got EI and the ER, HI and the HR. Add these two functions and equal to the 0, because E1 is equal to E2 bar. E2 is a 0 there. E1 is equal to the combination of incident and the reflected beams. Incident and the reflected beams. So EI plus EI bar plus ER bar is equal to E1, or H1 bar is equal to HI bar plus HR bar. HI bar plus HR bar. You can do anything. Okay, and simplify the equation, and to find out what is a E1 bar, the combination of the two functions, and find out the H1 bar, the combinations of the two functions. Okay, write it down that one. Those two equations, E1 bar and the H21 bar, is a horizontal polarization of oblique incidence at a plane of dielectric and the conducting or conducting medium. Okay, the equations of E1 bar with the combination of EI and the ER, and H1 bar with the combinations of HI and HR is the equations for the horizontal polarization of oblique incidence at a plane of conducting boundary. And in the tomorrow class, we see the vertical